Hello everybody, I'm going to do some calculations right now for Gibbs free energy as well as some more entropy calculations. We have this formula which I would say is one of the more important formulas of the semester, delta G equals delta H minus T delta S, that we derived pretty easily last time from the equation for delta S universe. This was a measure of spontaneity, which is discussed around page 8 or 9 of your note sets on Gibbs energy and entropy. I figured we'd do a calculation. There's some more calculations in your notes and certainly in the skill builder. We have a reaction here. It's a water forming reaction where we have hydrogen gas and oxygen gas forming liquid phase water. We're going to do it under standard conditions. So which that means that the gases each have a partial pressure of 1 atmosphere, and it will be at a temperature of 298 Kelvin. Remember, your standard conditions are not defined by temperature, they're defined by pressure, and the water is pure liquid water. So they're defined by pressure in the state of the material. So we can readily write this equation. We could calculate, really these are standard delta G's and delta H's and delta S's. It's the same principle. Just put a little not symbol, a little zero symbol there. So one of the things you'll always note when you're looking up in tables or you're getting data on things, we tend to scale things to make them look nice, is energies like enthalpy very often are in kilojoules per mole. And if you have an entropy that happens to be molar, which is in this case, they very often, they're usually smaller numbers. So they're usually scaled in joules, in this case joules per mole Kelvin. And so you have to be aware of that when you do the calculations to get common units. Let's calculate at, let's see what temperature I want to do this at 25 degrees Celsius. I'll keep a couple places behind decimal. Let's say it's 25.000 degrees Celsius. We can convert that to Kelvin. Let's calculate delta G standard. So you just basically plug into that equation. Delta G naught is equal to, we'll put it in kilojoules, negative 571.6 kilojoules per mole. We have the temperature in Kelvin. Need that, can't put it in Celsius, it won't work. Then we have the entropy, the molar entropy, negative 326.7 joules K mole. Mole K doesn't make a difference, the Kelvins cancel. We have to convert those joules to kilojoules. So there's 1,000 joules in a kilojoule. So that converts, we get rid of the joule part. Now we're in kilojoules per mole is going to be the units, and I calculated out here negative 474.2 kilojoules per mole. Check my math. That means it's spontaneous under standard conditions at 25 degrees Celsius or 298.15 Kelvin. Let's look at this process. It has one thing working in the favor of spontaneity, and that's the negative delta H, which means it's exothermic under these conditions. Conversely, because we're going from 3 gas molecules to liquid, we have a negative delta S in the sense of working against us. It's not working in the direction of spontaneity, especially at higher temperatures. So at higher temperatures, there'll be a certain temperature at which the right-hand term here, which will be a negative times negative is positive, will override that negative delta H. So let's figure out that threshold temperature for this system. So we have this equation, delta G equals delta H minus T delta S. So let's set it, the way I would do it is set it to 0. Set this equal to 0, because that's the interface between something being positive and negative is 0, right? So if we figure that out, any temperature above that threshold value will be non-spontaneous, and any temperature below it will be spontaneous. And so we have that. That's going to be equal to delta H naught minus T delta S naught. So we can solve for T. T is going to be delta H naught over delta S naught. And we'll plug in some values here. Negative 571.6 kilojoules per mole. We can have to change one or the other. It doesn't make a difference which one we change. Negative 3, the negative and negative is going to give us positive 26.7 joules per mole Kelvin. I converted the kilojoules to joules to have common units. Doesn't make a difference. As long as I get something, 1 kilojoule is 1,000 joules. So when I solve this out for T, all that's left here is going to be the Kelvin, which is in the denominator of the denominator. So we'll go up to the numerator. I got 1750 Kelvin. You can convert that to Celsius if you care to. Any temperature above that, it will be non-spontaneous. And temperatures below that, it will be spontaneous. And so that's a basic calculation type that you can do. You can calculate delta G. You can see is it spontaneous at 25 degrees Celsius. Excuse me, at 25 Celsius, 298 Kelvin. It's below 1750, and we showed explicitly that it was a negative value. I guess I erased it. It was what was the value for it? It was negative 474.2 kilojoules per mole. It's a negative number, is the big point. And so those are the type of calculations that you should be able to do. So I'm currently on page 9 in notes if you're following along. So again, we just did a problem where we had the little 0 naught symbol. So we have S naught and delta S naught and so forth. So we're going to call this a standard molar entropy. The one of the things is that I just want to make sure everybody knows this is from last semester. This is a review, but when we talk about standard conditions, what do we mean? For a gas, it's 1 atmosphere pressure for that particular gas. So for a liquid or solid, it means it's pure, like pure iron or liquid water. And if it's in solution, there's different conventions. I'm going to use the one the textbook uses. We'll say it's 1 molar. There are conventions where they use 1 mol. And there's also conventions where they use 1 bar of pressure, but it's very close to 1 atmosphere. Standard conditions are independent of temperature, but they do vary with temperature. So that's the thing, is that when we work with tables, I have what you can go access. I put online thermo tables in one of the folders. That those tables have in them standard molar entropy values, and so you have those. One of the things that I just want to take note of before we go on, this is the basis of allowing us to do certain type of calculations. We have 3 big laws in thermo. Last semester, we introduced the first law. I'll just put them in mathematical forms. And we could say that's, for a reaction or a process, the change in internal energy is equal to heat and work It's really a restatement of conservation of energy. You could say the second law deals with spontaneity, and we showed that for processes that are occurring, delta S universe is greater than or equal to 0. So you could say in words, you could say the entropy of the universe is never decreasing, is another way of saying that for any process that's observed. And then there's what they call the third law of thermo. And so the entropy of a perfect crystal is 0 at T equals 0 Kelvin. Absolute 0, that's not okay. The temperature's okay, it's 0 degrees Kelvin. 0 Kelvin, actually, it shouldn't say the word degree with it. At absolute 0, the entropy of a perfect crystal is 0. I would consider this to be a theoretical condition because A, we've never achieved that absolute 0 and it's arguably impossible to achieve. And number 2, the idea of a perfect crystal is A, a crystal without defects. You could see making that perhaps. But then there's other issues like issues with spin and other issues that really make the idea of a perfect crystal where you can only have one arrangement of things is either impossible or exceedingly difficult to achieve. So this has never actually been directly demonstrated. I consider it a limiting case law where you take things to the nth degree of where you could get them and this falls out. But this has some utility. It allows us, when you go to tables, we can list absolute entropies for things. And so you can actually just list the entropy. Energies are always, we always define an arbitrary and convenient point that's our 0 point to measure energies relative to, and sometimes we have to adjust for that. With entropy, there's actually absolute entropy values that exist for materials, and you can find them in tables. So you can go in the back and you'll find in your appendix standard molar entropies that are not by convention being defined to be a certain point. They're being measured relative to the third law. And so there's some trends with standard molar entropies, and I sometimes put a subscript M there. I'm not going to do it, but we'll just say these are per mole. And so for a given phase, and this is summarized on page 10. So for a given phase of a material of a certain type, it has to be the same material. I'll say substance, it's a better word. So the solid phase will have a lower molar entropy than the liquid, lower than the gas. It's usually a lot lower. I'm going to put 2 arrows indicating the gas is usually a lot lower, a lot larger. So this would have the largest molar entropy and it's the smallest, and this would be larger by a lot. So this would be like ice, and this would be, for example, could be liquid water. And this here could be water vapor, steam, if you will. And again, the entropy of the molar entropy, it means per mole of gas phase water would be a lot bigger than a liquid, which would be somewhat bigger than a solid. So that's one trend. With noble gases, we always like to talk about them because they're not very reactive and they're well known. So we have the noble gases. What do we have? We have helium, neon, going down the period, right? Periodic table in front of me, neon, argon, etc. ... It's not obvious. You might think that something bigger, slower would have higher molar entropy, but the larger, meaning the deeper in the deeper down the group you go, the larger the noble gas, the higher the standard molar entropy. That should be in the That's really a quantum mechanical effect. I actually derived this in thermo when I teach that course, not thermo and gen chem, and it involves stat mech. But I'll say this, it's basically because the heavier species, like down here somewhere you have xenon and so forth, have their, they don't, these are atoms, they don't have rotation and vibration. The translational aspect of them is what gives them the entropy, and the relationship comes out to suggest that the energy spacings between translational states are much closer together for the larger species than they are for the lighter ones. And that's purely a quantum mechanical effect, and so that allows more states to be accessible translationally. Translation can be looked like a continuum like classically, but it's actually a bunch of really closely packed quantum mechanical states. And so a big heavy Nobel gas atom, I was going to say molecule atom, has a lot higher standard molar entropy. You look at the table, I don't have the numbers in front of me, but these are substantially higher than their lighter the lighter elements on this list. So this increases as you go down the group, and so that's another rule. With allotropes that we learned about last semester, you'll have the more constrained allotropes. So we have allotropes like, for example, diamond and carbon graphite. The more constrained it is, for example, diamond, again, I'm not a good artist here, but I'll just draw something kind of imagined kind of diamond, something like this type of thing. We have internally inside a diamond, you have a really tightly packed lattice. As you can tell, diamond's very hard. It's hard to chip diamond and so forth, versus graphite. Graphite is like, on a small level, is a bunch of sheets. They look like chicken wire almost molecularly. They have a lot of degrees of freedom. Those sheets, this is what gives it a lubrication property. So this would have a higher entropy, molar entropy, than diamond. So graphite, for example, has a higher standard molar entropy than diamond. Those are the two main allotropes of carbon. There is a third called the carbon-60, and I would think it would be intermediary to that, but I could be wrong about that. So these are definitely two extrema. Just useful calculation type is if you have a reaction, just A of a certain phase. I'll just put a bracket here representing some type of phase, because the phase will be important. I don't want to necessarily it's a gas, but there's a phase of this going to C gas. And let's just say there's coefficients here. It could be 1s and 2s or what have you. Coefficients of a balanced reaction. If you want to calculate out the standard molar entropy of that reaction, it's doable. And so you just go to your table. I'll just put Rxn to mean for a reaction. We go and we use the same form of products, just like you calculated last semester, standard molar enthalpy, for example. Well, in this case, we just have the stoichiometric coefficients of the balanced reaction, just the numbers, if we want to get in molar terms. And we look up on the table the standard molar entropy of the products. And I'll just we're summing over them. I'm not going to put an index, but we're summing over all of them. Then we have, for the reactants, the coefficients of them, and you have this whole thing, you're going to be subtracting this. So these are the reactants. And where do you get these? You get these again from the thermo table. You don't have to memorize them. They're always positive values. The molar entropies are always positive, and they're always greater than 0. So they're different than the energy ones where you get a lot of zeros for elemental forms. So let's just go do an example. So we'll use this equation here. I'll work one of the ones in note sets. And again, these numbers are not coming out of the blue. You just look them up on the table. And so for a solid state reaction, let's just pick that. I just if it's convenient. 2 aluminum solid. Just want to make sure you can see this. Good, you can see it. And 3 zinc oxide solid goes to alumina, Al2O3 solid, and 3 solid zinc. Solid, let me make sure it's balanced correctly, because if it's not, I'll do a problem that'll be a waste of time. 3 zincs, 3 oxygen, 3 oxygen, 2 aluminum, 2 aluminum. We're good, and there's no charge on either side, so there's nothing to worry about this. So you go to the tables. I'm just going to write the values that I saw here. These would be SO. These would be the molar entropies in units of joule mole Kelvin. So when we write something like this, where the interpretation of delta S naught of reaction per mole is per mole of reaction unit. So each aluminum on there is 28.3, and hopefully I didn't get a little, sometimes I see numbers backwards, 43.9, 50.94, 41.6. It should, if you see a negative number, you're in the wrong column. So, because these will always be positive numbers. So, let's do the products minus reactants, delta S naught. For reaction, I'll do, this will be the products. We're going to have, which one did I put in here first? Here we got zinc. I have in here zinc is 41.6. We got a 3 in front of it. I'll put the joules per mole on the outside. And then we have 1 alumina, 50.94. This is in joules per mole Kelvin. I would always put parentheses around it, particularly the second part, because in this case, this is a thermodynamic calculation where there actually are no minuses, but with enthalpies, is always you always have the potential for a minus of a minus and so forth. It's just a good habit. That's how I do it. Let's see. We have aluminum. We have 2 times 28.3, and then we have what else do we have here? We have 3. Hopefully, I don't make a mistake here. Times 43.9. Go to the tables, verify these numbers, and this is joule mole Kelvin. Forgot, ran out of space there. That's mole Kelvin. So when I do it out, I got negative 12.6 joule per mole Kelvin. While S itself can be, it has to be positive. Delta S can be positive or negative. I look at this, it's really hard with this solid state reaction, because everything's a solid, to justify why it's a small negative number. It's a very small delta S of reaction. I'd have to really think about the solid state structure of all this. It's not obvious, and so it ends up being a very small number, slightly on the negative side. So that's a real simple type of reaction. We also can calculate out, let me just leave this. Well, we're actually running out of time, so I'll do the last part here in the next video. We'll pick up with calculating delta G naught of reaction in a future video. So thank you and have a good night. Just right in time.